Okay, and so how do we calculate now the rate of change? So what is our dx is, wow, small, 0.00, how many zeros is that? Dizzy, is it 5? Two, three, four. Okay, and so how do we calculate, that was supposed to be, how do we calculate that constant rate of change? Change in y over change in x. Okay, but then the program that you had did that for you, and you're analyzing how did it do it for you. Okay, so here's that. We were making sense of this formula right here that was doing it for you. So how is that top thing the change of y? Well, it's the final value of y, which is g of that 2.753 plus dx, minus the initial value of y, which is that g of x naught minus dx, over 2 dx. So hopefully you made sense of that as a way of calculating dy over dx. And so then it automatically does it for you. M is negative 1.747. Why? Because we set it up to do that for us. Okay, so the moral of the story is, can we get a moment small enough so that the graph is essentially linear? And if we can, then we have a rate of change at the moment, and we calculate it by dy over dx within the moment. And that gives us that constant rate of change. Okay, so rate of change in a moment is a constant rate, right? It's a constant rate. We're looking for a linear, small enough piece of the curve that's linear. Okay, questions on that? So let's look at this. Do we have rate of change in a moment for this graph? What's that? Okay, so what about at 0.5? Will we have rate of change in a moment there? Sure. If we zoom in, and we don't have to do much for this. Well, it's almost linear now, right? So this is at 0.5. So at 0.5, I zoom in twice, essentially linear. Rate of change in a moment, we could find two points, find dy over dx. Okay, so is that true everywhere for this graph? So obviously there's something that's going on here. At 1, we have what's called a cusp or a corner point. Do we have rate of change in a moment at x equals 1? If we do, then what? We should be able to zoom in far enough so that the graph is essentially linear. But we got to keep it containing x equals 1. I'm going to just keep zooming in here. What are we trying for? We want to see the whole screen with a straight line. We want to see the whole screen with a straight line, meaning constant rate of change over a small enough interval. It's never going to happen. You see this? It's never. Look at the scales now. You can't. It's so. No, you can't. No. Okay, don't get too excited. There we go. Yeah, so I've zoomed in so much that graphing calculator can't even distinguish what the values are on the scale anymore. It's showing 1. Okay? All right. So the point is that when you have a sharp corner or a sharp point in a graph where the rate of change changes immediately, if that's the point in question and you keep zooming in, you can never get a rate of change in a moment. Okay? So for this particular graph, a rate of change at a moment exists at every x value except x equals 1. What about 0.99? Yeah, what about 0.999? Yeah, as long as it's not 1, we can get far enough into it so that that cusp is out of our moment, right? So we just zoom in far enough so that the cusp is outside of our moment interval, and then we'd show a constant rate of change. All right, so how about this? So now the red graph is a line that I can manipulate the rate of change, okay? So looking at this, I'm at 1.215. At 1.215, do you think that the rate of change is positive, 0, or negative? Positive, 0, or negative? Place your bets. Place your bets. Ready? Positive, 0, or negative? Uh-oh. It's negative. Okay, let's keep zooming in. Here we go. If you said negative, good job. Here we go. Ready? Oh, whoa. Oh, uh-oh. It's positive. Here we go. Wait. Let's just confirm that it's positive. Here we go. Oh, maybe a little more positive than we thought. So like that. Okay, that's it. So let's just confirm that. Here we go. Okay. Oh, what? Oh, so it's like 0. It's 0. It's got to be 0. Or so maybe just slightly positive. What? It's negative. Okay, so this is a really cool function because it has rate of change at a moment, nowhere. There's nowhere where you can zoom in where it will smooth out. It's got every single x value is a cusp. You keep zooming in, and it just keeps, because it's still always jagged at whatever x value you choose. Want to see some more? Oh, positive again. So no matter how much you zoom in, it always looks like a cauliflower. It's always jagged at every x value. But some people are thinking, no, you got it, now you got it. Oh, I didn't want that. That's fine. Just one more try. One more try. Maybe. Wishful thinking. Okay, so now we've zoomed in so much, GC can't handle it anymore. Okay? And it's still jagged, right? It's still jagged. So the point is that this, it's breaking down. It's breaking. GC can't graph this small. So this function is called the Blancmage function, and it's a complicated function that results in cusps everywhere. It's jagged everywhere. You can't zoom in anywhere and get a rate of change in a moment. Okay? We're not interested in these in this semester. Okay? If you think this is cool, then it's sort of higher level math. Okay? But the point is that rate of change in a moment is if you can get a small enough interval so that the curve smooths out, flattens out into a little linear piece, so that you have constant rate of change. Okay, what's next? Any questions on that? All right, so we need these handouts. Can you help me hand out stuff, please? That's for the first 2 rows. Okay, so we're gonna continue with the Usain. So while we're passing those out, let's watch something fun here.
Where's your fork? Where's your fork? I don't know what happened to your fork. Where's your fork? Oh, what do you eat for dinner? Pasta. Is it good? And what are you using to eat the pasta? A fork? A fork, yeah. Where's your fork? There it is. Can you show us how you can use your fork? Can you show us how you know how to use a fork? Very good. Remember what Grandma showed you? Oh, yeah, that's right.
Did you see it at the beginning? It was there the whole time. Okay, so that was my daughter Emma, like, I don't know, a year and a half ago. Maybe we'll show another one sometime, but that's an oldie but goodie. Didn't go viral, unfortunately. Should have. Okay, so you got your hand out there. So we're going to continue with the Usain. This is the Usain activity. Okay, so the first part of this is review, and then part 2 is where we're going to get into a really important idea. But so let's just do some review first. So what I want to do first is look at row 1 in the table, row for x equals 1. So notice that first column is telling you C, the current value of x. So I'm going to change C here to I'm going to try to change C to 1. There, I got it. Okay, so C is 1. Okay, so we're at C equals 1. And so we want to get the next column is the moment, x equals C. So we're going to get a moment such that we'll have a rate of change in a moment. And then we're going to pick a differential dx. And then we're going to have 2 correspondence points. And then we're going to calculate the rate of change. Okay, so it's all review, right? All review. So I'll come in here and I'm going to zoom in. Okay, and so is this moment good enough to get us a rate of change in a moment? Curved, right? So we're going to zoom in here. How about now? Pretty decent. We could go a little smaller if you want. And then again, so I've got dx here. I can change dx, and then that changes my correspondence point. So let's just do 0. There we go. Let's make dx 0.015. So what would you say is the moment in question here? What's the moment in question? Moment is again a what? Interval. And so what's the moment in question? Like 0.975 to 1.03. 0.975 to 1.03 is the moment. It's the interval we're looking at such that we have, and in this moment we have constant rate of change. Okay? What is dx, the differential in x? Fill it in. Okay? What's our first correspondence point then? All right, so the function, this is this distance function, is f. The function is f. So I want you to write the coordinates of this first correspondence point right here. This is it right here. So this is the first correspondence point. And that's the one at x equals c. So how could you express the coordinates of that correspondence point? Of time since start and distance from the starting line. Okay? And then then the next, here's our second correspondence point. This is our dx. So how can you express that? And then once you have those two expressed, how could you calculate the rate of change at the moment? So my program is doing that. Okay, so it turns out to be 6.108 up there. See that? So for c equals 1 and dx of 0.015, we get a constant rate of change of 6.10816. So you're going to express the coordinates of those points in that row for c equals 1. And then you can just write down 6.10816 because I didn't give you the function. Okay? So what you're going to do, any questions on that first row? That's an example. Okay? So what you're going to do, I'm going to upload a GC file that you're eventually going to download into your laptop if you have one. In the meantime, you're going to do a generic version of what we just did for the last three columns. So in this first column here, the one that's taller, you're going to do these three right here. Okay? You're going to do those three things right there generically for any value of c and any value of dx. So you're generically filling this in for any value of c and any value of dx. Okay? Is the task clear? And if you haven't finished row 1 yet, finish row 1. Finish row 1. And then after that, you're going to generically put in how you would get the first correspondence point, second correspondence point, and the rate of change at the moment, x equals c. Okay? And then in the meantime, I'm going to upload the GC file so you can download it. Go. Get help if you need help. The situation we did for c equals 1. We said the moment was what? 0.975 to 1.03. Write it down. In the moment for c equals 1. 0.975 to 1.03. That's the interval that we're looking at for c equals 1. That's the moment. Are we good on that? And then I just decided it didn't matter. I could have done something different. But we came up with dx of 0.015. dx varies within the moment. It's smaller, right? So it varies within the moment. So here's dx of 0.015. Write it down in the dx column in row for c equals 1. dx equals 0.015. Okay, so now to calculate the rate of change, we need two correspondence points. We need a time and distance and another time and distance. That's going to be determined by our dx. So this is the first correspondence point. It occurs at c equals 1. So how would you represent the distance at time equals 1? If c equals 1. Right. Anyone else? How would you represent the distance from the start line at c equals 1? Function notation. What will it be? F of 1. Everything we've done is important. Everything we've done is important. So now we have this other correspondence point. What's the x value of that correspondence point? 1.015. It's what? 1 plus dx. 1 plus dx. How would you express the distance traveled after 1.015 seconds? F of 1.015 seconds. Now you've got the two correspondence points. How would you calculate the rate of change at this moment? Then what would you do? dy over dx. And I told you, you can't get those numbers just with what you have because you don't know what the function f is. So you could represent that, the f of the 1.015 minus f of 1 over the change. And then I told you that value is 6.10816. My GC file is calculating it. Questions on the row in the table for c equals 1? Is it better? Question, yeah.
So the second correspondence point is at 1.015.
That's not a correspondence point. That's just one value. So what would the correspondence point be? It's an ordered pair, right?
Yeah, that's all. Second correspondence point is
Would be what? No, but that's just a value. A correspondence point is an ordered pair. It's simultaneous values of two quantities, right? It's an ordered pair. So what will it be? That second correspondence point. It's an ordered pair. It's an x value and a y value together. An ordered pair. 1.015, comma, f of 1.015. That's a correspondence point. The correspondence of a time and a distance from start. Together. You see? Okay, more questions about row 1? Yes, please.
So, like when we did it for the 1.0,
Yeah.
the dx, is that like the whole moment from 0.975 or just 1 to 1?
Yeah, so the moment is this. The dx is I'm showing by this pink arrow. That's dx. And I've selected it on my slider up there. dx varies within the moment. Remember that? Other questions? Yeah.
first correspondence point is 1, comma, f of 1.
Right. Correspondence points. You take an x and a y, a corresponding y, for a relationship, a function, and you put them together. That's a correspondence point. What is this graph? What does it consist of? All the correspondence points. All of them. How many are there?
Infinite.
How many in this moment?
Infinite.
In just this in the moment, there's an infinite number of correspondence points. And I could make a smaller moment and still be an infinite number of correspondence points. Okay, so now the file, the GC file, you should have opened that up by now. You have some tasks. So what you're going to do is you're going to make listen up. So now you're going to kind of make the same file that I was just showing you that automatically you pick the C, you pick the dx, and it calculates the m for you. So you have 3 tasks. The first task is display the graph of f. I've given you I've defined the function of distance from the start versus time from the start. You need to display that graph for the time that you spent running, 0 to 9.58 seconds. Hopefully remember that. Task 2 is plot the 2 correspondence points, but generically for any c and any dx. So that we just talked through that, but now it's generically for any c and any dx. You're going to plot those 2 correspondence points. That's your second task. Okay. Third task then is to write the formula based on those 2 correspondence points that will calculate m. And then you can go back to the slider and change c and change dx, and it'll tell you m. And that's how you're going to finish building the table. Questions on the graphing calculator 3 task deal? Yeah. Okay, here we go. Okay, for c equals 3. So I'm going to type in, you could just type in c equals 3. Okay, there's c equals 3. So what do we want? We want to get a moment around c equals 3, right? A moment contains the point x equals 3. Such that, and we want, our goal is the rate of change at the moment c equals 3. That's our goal. Our goal is the rate of change at the moment c equals 3. So we're going to zoom in. Okay, so does the graph look linear in our view? Okay, so this is a valid moment. So what's the moment? It's the interval we're looking at. you could have a different answer. But I came up with 2.86 to 3.16. That's the moment that I'm showing. Maybe yours is a little different. Okay? Now, what happens? dx varies within the moment. Okay? So for this one, I'll set it at 0.45. Okay? 0.045. So that's dx equals 3.045. No, just 0.045. If you built the file correctly, now you've got your value of c, 3, you've got your value of dx, 0.045, and it's giving us the rate of change, 10.8. And what's the units on that? 10.8 what? What's the dependent variable measured in? Meters per second. So we could say, at 3 seconds after starting to run, Usain is running 10.8 meters per second. Does your GC file give that value? Okay, so let me show you. What's the first correspondence point? Generically, for C, the first correspondence point will be C, comma, f of C. First correspondence point. What's the second generic correspondence point? What's the x-coordinate of that point? The x-coordinate. C plus dx, right? It's dx later. What is the distance at that time? F of c plus dx. So your second coordinate point is that. And now you've got the two generic coordinate points, so you can just make an expression, change in y over change in x. Change in y is? Will be the final value of distance minus the initial value of distance. And the change in x is, you don't have to do a subtraction. You know the change in x. What is it? You don't have to subtract anything because you know what the change is. What's the change in x? No, generically, to make the formula. Just dx. Just dx. So given a point in question, you want to know the rate of change. That's c, and given a value of dx that's small enough within a moment, this will then calculate the value of m, and so then we go back up here, and it tells us that m is 10.8 meters per second. So now what I want to do to move forward is, so questions about that. That's the rate of change at 3 seconds. Anybody have a question? So I realize, yeah.
To get the rate of change more exact at 3 seconds, for example, would you just make the dx smaller?
Sure. So he's asking, do we want, so this is linear, and then we're even taking just a little dx right there. So this is going to be really close, but if you wanted it even closer, what could you do? Make dx smaller. So here's dx of 0.0105, and you have a slightly different rate, 10.78. Slightly different. But so you're all could have different numbers. But it should at the end of the row 3 for the rate of change, it should be somewhere around 10.8. Everyone should be somewhere around 10.8. Questions on the row with time equals 3. So let's hopefully maybe someone's done, or as a collectively we got this whole thing done. Okay. Anyone got 0.25? Someone just write down the rates of change. We want to move on. So what did you get for 0.25? 2.18? Anyone get 0.5? 3 point? 1.0, we got 6 point something? 6 point? 1. Anybody get 1.5? Nice and loud.
7.9,
Thank you. Anyone get 2?
9.2,
2.5.
10.1,
And we just did 3. What was 3? 10.8. Anyone get 5? Nice and loud. 11.8? These sound right? Okay. Anyone get 7? Cool. And finally 9. Seven? Okay. So if you want it, so you've got your GC file. Make sure you save it. You can experiment later and practice with different rows that you haven't done. But we want to move on. Here's a question. Change in y over change in x based on your 2 correspondence points. Right? The change in y from your 2 correspondence points divided by the change in x. Yeah. Question?
So we were trying
Okay,
to,
shh.
so we were trying to figure out how you guys got c and dx, but then like we were able to put in the points, but we didn't get those exact answers.
No, right. Everyone will have something a little bit different.
Okay.
If you're just close to these, you're good.
Oh.
Because people have different moments, people will choose different dx's,
Oh, okay.
and that will affect that rate of change a little bit. You may have slightly different answers, but they should be close to this.
Yeah.
Choosing a different dx, okay, listen, choosing a different, so we're maybe in like get the right answer mode. That's not the point of this. The point is understanding what's going on, and a different dx will result in a slightly different rate of change.
So the dx changes the like.
Yeah, because it's that m formula, the m formula you wrote has dx in it.
Right.
Change dx, you get a change m. But if we're small enough and we got rate of change in a moment, it should be close.
Okay. Yeah.
It should be close. Awesome. Good questions. Other questions? So my intention was that was kind of review, and that was going to take a little less time. It's okay. I'm glad that we hammered it out. Really, question 2 is now starting kind of a new idea. And the new idea is we're going to make a new function called the rate of change function. The independent variable is going to be c. It's going to be the same. It's not c. It's going to be x. It's going to be the same x we had before. Time since the start. And now the dependent variable is not going to be the distance from start anymore. The dependent variable is going to be the rate of change. So we're building this function that has the same independent variable, time since start, and the dependent variable now instead of distance is rate of change. So you're going to start by just plotting these correspondence points, and we're going to call that function r sub f. R sub f, you see there in number 2. It's a new function. The independent variable is the same, x, but now the dependent variable is the rate of change of Usain as he's running. So we're going to start by plotting these, 8 or 9 correspondence points for that function. So that's on the axes below. So on the axes below is going to be, we're going to build the function, a displayed graph of the rate of change function. So the y values, this is key, the y values on this graph are no longer distance, they're rate of change. Go. Can you do it? You're just plotting these points. You're plotting these, 8 points. Same x values, new y values, which are rate of change instead of distance. You're plotting those points. Is the task clear? It's an easy task, but it won't be easy if you don't understand the task. Is the task clear? Once the task is clear, this is easy. Okay, so this new function that you're plotting, we're first going to plot individual points. The x values are the same x values as the previous function, time going by since start. But now the y values of these points are not distance from the start anymore, they're the rate of change. Okay, so here are your x values. For instance, you're going to plot the point, 0.25 time, seconds, and 2.18 meters per second. You're going to plot that point on the new function, the new graph. And then you're going to plot the point, 0.5 seconds, and what was this rate of change, 0.5 seconds? 3.7 meters per second. 2, 3, 4, 5, 6, 7, 8, 9. You're going to plot 10 points. You're going to plot 10 points on those axes below. This is going to be a rate of change function as opposed to a distance function. I see lots of people doing other things besides plotting points. You should be plotting points on the paper I gave you. Can you give me 3 or 4 more minutes, and I'll give it back to you another day? So you should get something like this. I know this is exactly right, but you should have gotten something like this. Did you get that? I'm just guessing. I don't have the points right, okay? I don't have the points right. How many points? So what did I just do? I just drew an infinite number of correspondence points between time from start and what's the dependent variable? Rate of change. How fast in meters per second he's going. Okay, so there's one more task left, and that will. Okay, so I reproduced. So my daughter Emma. So she's a runner too. Okay, so but we're doing something after this. It's not an entertaining thing at the end. Okay, so but she ran at 10.7. Go, you can do it. You can beat him. Yes, beat him. All right. So what is she doing? So I reproduced his race, and what's her rate of change like? What is it like? Constant. She's running at 10.7 meters per second, and so she beats him. She's fast, okay? She's fast, all right? So what I want you to do is, on that rate of change graph that you just drew for Usain, for his race, I want you to draw the rate of change graph for Emma. In addition to, so put it on the same axes, what would Emma's rate of change graph look like? She runs at a constant rate of 10.7 meters per second. She runs at a constant rate 10.7 meters per second. So what would her set of correspondence points look like for time and rate of change? All right, so what does that graph look like? Horizontal line, a constant rate of change on a rate of change graph, no matter what the time is, it's the same 10.7 meters per second. Okay, thank you for staying late.